Hi, I'm Agustin Raiо. I'm an associate professor of philosophy at MIT. And today I want to talk about how there are some infinities that are bigger than others. So we've seen that there are a bunch of infinities which are really the same size in the sense that they can all be put in 1-1 correspondence with one another. So one might be tempted to think that all infinities are the same size, that any two infinities can be put in 1-1 correspondence with each other. But in fact, that is not true. And that is the second big theorem that Kantor proved. What he showed is that there are more real numbers than natural numbers. So, if as many new guests as real numbers showed up to the hotel, we could not accommodate them. In fact, we couldn't even accommodate them if the hotel was empty to begin with. So here's how to do it. What we're going to prove is that there are more real numbers between 0 and 1 than there are natural numbers. And the way we're going to prove it is by reductio. We're going to assume the opposite of what we want to prove and derive a contradiction from that assumption. Because the opposite entails a contradiction, it can't be true. So the thing we wanted to prove must be true. So what's the opposite of what we wanted to prove? Well, it's the idea that the real numbers between 0 and 1 are in 1-1 correspondence with the natural numbers. So it means in particular that we can assign a different natural number to each real number between 0 and 1. So assume that's true. Here's a diagram representing that. Each real number between 0 and 1 can be represented as a decimal expansion. You can write it as 0 point and then an infinite sequence of digits. So suppose that we can assign a different natural number to each real number between 0 and 1. So here's an example of how that might go. To the natural number 0 we assigned this real number, and to the natural number 1 we assigned this real number, and so forth. Now what we're going to do is we're going to use our list to create an evil number. And here's how we do it. First we consider the diagonal, which is just a result of writing 0 point and then the sequence of digits which we get from this diagonal here. And once we have the diagonal, we define its evil twin. The evil twin of the diagonal is the number that you get by writing a 7 whenever the diagonal had a 3, and writing a 3 whenever the diagonal had anything other than a 3. So here's how it would go. So here we have a 3, we write 7. Here we don't have a 3, we write 3. Here we have a 3, we write 7. Not a 3, we write 3. Not a 3, we write 3, and so forth. Kantor's observation is that the evil twin cannot be on our list. Why can't it be on our list? Well, it can't be the first member of our list because the first member of our list has a 3 in its first position, but our evil number has a 7 in that position. What about the second one? Well, it can't be the second one because the second one has something other than a 3 in its second position, and our evil number has a 3. And generally speaking, the evil number can't be in the nth position, because whatever the number in the nth position has as its nth digit, the evil number will have something different. So here's what's happened. We've assumed for reductio that you can assign a different natural number to each real number between 0 and 1. But then we found a real number, the evil number, which isn't on that list. It contradicts our assumption that we really had assigned a natural number to every real number between 0 and 1. So our assumption must be false. And because what we assumed is the negation of what we wanted to prove, it follows that what we wanted to prove is true. There are more real numbers between 0 and 1 than natural numbers. So we've identified two sizes of infinities so far. The size of the natural numbers, which we know is just as big as the size of the natural numbers plus one additional element, and just as big as the size of as many copies of the natural numbers as there are natural numbers. And we've identified a bigger size, the size of the real numbers between 0 and 1. Are there other things which are that bigger size? As it turns out, yes. There are exactly as many real numbers as there are real numbers between 0 and 1. And there are exactly as many points on a line as there are real numbers. And there are exactly as many points on a plane as there are real numbers. And there are exactly as many points on a cube as there are real numbers. And there are exactly as many points in a hypercube as there are real numbers. So, is the infinity of the real numbers the biggest infinity there is? As it turns out, there are infinitely many sizes of infinity. Another thing Kantor proved is that whenever you have a set, the set's power set, in other words, the set of all subsets of the original set, is bigger. So the power set of the set of natural numbers is bigger than the set of natural numbers. And the power set of the power set is bigger than the power set. And the power set of the power set of the power set is bigger than that. And so forth with no end.